On this video, which is the third video for chapter 2, we're going to talk about section 2.4, which is about quantiles and normal quantile plots, right? So first some definitions, which should be mostly a review from Math 313, right? Let's suppose we have x, which is a random variable, so it has some distribution. And then we're going to pick a probability value between 0 and 1, and we're going to define what the pth quantile of x is. So the pth quantile of x is the value q sub p such that the probability that x is less than or equal to q sub p is equal to that selected probability, right? So if you happen to know, let's say, the PDF of x, let's sketch it. So little f is going to be the PDF of x. Q sub p is the point where, if we shade to the left, this shaded area is equal to p units of area, probability p, okay? Or in terms of calculus, p is equal to the area underneath the PDF from negative infinity to the spot q sub p. Or if you want to use the CDF, capital F capital F at q sub p should return the value of p. Or q sub p is capital F inverse of p. It's the inverse of the CDF, okay? All right, so that's where capital F is the CDF, the cumulative distribution function, and little f is the PDF, the probability distribution function. Okay, so let's do a little example with perhaps our favorite distribution. I'm going to let x be an exponential distribution with lambda equaling 1/5. So please recall that would mean that the expected value of x is 1 over lambda, which is 5, and the variance of x is 1 over lambda squared, which should be 5 squared. Okay, so just not important for this problem, but just recollections from 313. All right, so x is exponential, lambda equals 1/5, and I want to find the 0.4 quantile. So I want to find the spot where 40% of the probability is to the left of that spot for this exponential distribution, okay? All right, well, I'll remind you, if I know it's exponential, I know it's PDF. So its PDF would be 1/5 e to the negative 1/5 x, or e to the negative x over 5 for x greater than 0. And the CDF would be 1 minus e to the negative x over 5. And again, for x greater than 0. You should know the PDF and the CDF for an exponential distribution. That should be memorized, so should this, okay? All right, well, if I'm trying to find q sub 0.4, I'm looking for this value of q where the CDF is equal to 0.4. So there's my CDF with this q plugged in. I'll set it equal to 0.4. I can add the e term to the other side, subtract the 0.4 to this side, so I get the e is equal to the 0.6. Take the natural log of both sides and multiply both sides by -5. And I get q sub 0.4 is equal to 2.55. So the 40th percentile, or the 40th quantile for the exponential distribution when lambda equals 1/5 is at 2.55. So 40% of the probability of this exponential distribution occurs less than in the region to the left, 2.55. Right, so make sure you got all that copied down. I'll move over to the next panel. Pause it, copy it, go. All right, so next panel. So in red is stuff I'm going to do in R, or you're going to do in R sometimes. All right, so pause it, copy down that stuff, and I'll talk through it. All right, so oftentimes we're going to be needing to find quantiles for normal distributions. We like data that's normal, so we'll deal with normal stuff a lot. So in this example, I'm going to find the 30th percentile of a random variable that's normal with a mean of 3 and a variance of 4 squared. Okay, it's not the standard model. And so I'm looking for q.3. So by definition, this means I want the area to the left of q, the probability to the left of q, to equal 0.3. And if you remember from 313, with normal distributions, we love to standardize them. So we're back into an N01 distribution. So from the x and the q, I'm going to subtract the mean of 3 and divide by the standard deviation of 4. X minus 3 over 4 is now an a Z variable. It's N01 distribution. We standardized it. And I'm stuck with Q minus 3 over 4 there. But now I can go to my N01 table, my standard normal table, which hopefully you all have. Let me grab mine and just remind you what it looks like. But in the book as well. So when I look at this, whoops, a daisy, that tilted badly. Okay, so I'm looking for where the area is 30%, and I don't have it, but I do have where the area is 70%. So if I look for the 70% mark, it's in between 0.52 and 0.53. So 70% of the area is to the left of 0.525, let's say. Well, that would mean 30% of the area is greater than 0.525, which also means 30% of the area is less than negative 0.525. So by the symmetry thing, I get this minus 0.525 for my Q minus 3 over 4, okay? Or to say another way, to the left of negative 0.525, the normal distribution, standard normal distribution has 30% of its area. So Q minus 3 over 4 is going to be playing the role of minus 0.525. And when I solve for Q, I get 0.9, right? Now, in this class, I wouldn't have you do that. I would have you turn to R. So with R, I'm going to type in the following command. Q norm, no spaces, no capitals, parentheses, 0.3, that's my quantile, comma, 3, that's the mean, 4 is the standard deviation, and it returns 0.9023979. Now, those two answers are not the same, but like I was approximating via the normal table because I didn't see 0.7 dead on the nose. So that was a guesstimate on my part. So this is a better value for it. Okay, pause, copy. All right, next panel. All right, and here I will be turning to R at the end of it. All right, so now we're going to be looking at something called normal quantile plots. And so the general situation for these is, as will be the case in most of our problems in this class, we're going to be given a random sample from some data set, from some distribution perhaps. So I got a random sample, x1 through xn, from a random variable x. And I don't know how x is distributed. I don't know if it's normal, exponential, gamma, Poisson, no idea. I've got some data, right? So I'd like to test, though, whether or not the random sample looks like it might be normal, right? So we're going to test whether the random sample looks normal. And for this, I'm going to assume that I've already ordered my data from smallest to largest. So in the last video, I was renaming those as Y's, but let's just say you've done it. They're already from smallest to largest, okay? So how do we check if it looks normal? Well, we're going to plot some points. We're going to plot these Q sub k, X sub k. Now, the X sub k are from our data, x1 up through xn. And the Q sub k are going to be the k over n plus first quantile of standard normal distribution. And I'll illustrate this thingy in an example, okay? But it's the k over n plus first quantile. So if n is 9 and k is 3, that would be the 3 over 10, the 0.3 quantile, the 30% mark for n01, okay? All right, so we're going to calculate a bunch of Q sub k's. We're going to plot these points on a graph. And if these plotted points appear to fall on a straight line, we're going to conclude that the data follows an approximately normal distribution, okay? Now, when we do this on R is going to draw a line from the first and third quantile points. Those are the 2 points it's going to pick to draw the line. So it's going to draw the line from Q.25 to Q.75, or the closest it can find to those 2 points, okay? All right, so we plot those points. If they appear to be normal, we conclude that the data, x1 up through xn, follows an approximately normal distribution. If it doesn't appear to be normal, we're going to say, you know what, this data does not look normal, right? So this is one type of quantile plot we can do, or QQ plot. Now, if I wanted to test if the data was exponential, I could do a quantile plot with exponential quantiles playing the roles of the Q sub k's. right? Normally, almost exclusively in this class, we're going to do QQ normal. We're going to test to see whether something's normal or not. And that'll be the QQ plot command. Now, in your book, pages 33 to 35 have a bunch of really good examples of this. And I'm just going to do example 2.11 via R to show you how the commands work. And this R code is located in the file, in the R file for chapter 2. All right, so make sure you got this all down. I'm going to go screen share an R file. I got a screen share down. Okay, so if you scroll down a ways, you'll come to example 2.11. Now, in this example, we're given some data that's defined in some. So the data we're given are these numbers, 17.7, 22.6, all the way to 36. So the first step is to put them in a vector. So R knows what the data is. I'm going to call that vector X. Okay. So in the bottom left corner, you'll now see that X is going to reproduce for us. Line 54 now says QQ norm X. So do a quantile normal plot for X. So I'm going to run it. And you'll see in the bottom right corner, a normal QQ plot has appeared with some points plotted. And now you can decide for yourself if you think that looks like a straight line or not. The next command I do, QQ line X on line 55 in the top left, that's going to add a straight line, okay? And you can only run that command if you've already run the QQ norm command. If you've already created a plot, then you can run it. And so we can look at that straight line and say, you know what, it's not looking like a really good normal fit, right? The first few data points are way below the line. I mean, after that, it starts to look good, but it's not looking perfect to begin with, okay? Now, the way we're going to normally do this is we're going to call in a data set from the package, you know, our norm package. And I just want to make sure I'm still clicked on sample. Resample data still clicked, good. So we're going to take a look at a bunch of birth weights of babies born in North Carolina in 2004. And we're going to look at their weights, and we can ask, hey, are the birth weights normally distributed? So I'm going to do a QQ norm plot on the data set North Carolina births 2004, looking exclusively at the variable weight, baby weight, not height, not age of the mother or whatever else is in this data set. So let's run this command, which is on line 60. And we've got a new normal QQ plot. There's a whole bunch more data. And if you look at it, that's looking pretty straight. That's looking pretty linear to me. And if I could throw on a QQ line, there it is. You can barely see it in that bottom right plot because it's pretty much dead overall data points. So we can look at that and say, you know what? That's looking pretty darn normal to me, okay? All right, so that's how we can use R to figure out these normal plots or QQ normal plots. All right, we can also do it somewhat by hand. So the last panel is an example of doing this process by hand right over here. All right, well, by hand, somewhat by hand, let's just say. No, shift it that way. Sweet. Okay, so again, I would pause it, copy out the material there, and I'll jump in. Okay, so we're given a data set, the numbers up above here, and I've already put them in ascending order. Though that's not necessary if you do this all on offer, it doesn't need to be in order. So I got some data, and the question is, does this data look normal? Well, first off, I count. I've got 9 points of data, so my n is 9. That means for 1 through n, I need the corresponding quantile. So I need the 1 over 9 plus 1, the 2 over 9 plus 1, the 3 over 9 plus 1. Those are my k over n plus 1 quantiles. And if you note, it's the 0.1, 0.2, 0.3, up through 0.9. So it's the quantiles every 0.1, the 10%, the 20%, the 30, the 40, 50, 90%, okay? So I need to find those quantiles for N01, and I could guesstimate them from the standard normal table. Otherwise, I'm going to use this handy command in R. For Q.1, I'm going to do QNorm.1. Now, I don't need to specify the mean or the standard deviation as I did in the earlier panel, because if you don't specify them, R defaults to assuming you mean the standard normal, which is what we do for a QQ normal plot. So I'm going to do QNorm.1, QNorm.2, and I get all these values here. Okay, so now I'm going to plot these points. On my horizontal is going to be my standard normal quantiles. Those are the red values over there on the left. And on my vertical is my data points, my data quantiles, which is going to be the actual data. So here is Q.1, negative 1.28, comma, 0.05, the first data point. Here is Q.2, minus 0.84, comma, the second data point, 0.08, and so on and so forth. And this last guy is Q.9 at 1.28, and the last data point at 5.7. And if you look at it, I'm not going to try and throw in a line, but if you look at it, it sure doesn't look like the data points are falling. These plotted QQ points are falling on a line. So I'm going to say that this data does not look normal. And we should have expected that because it looks like the data is kind of crowded here on the left, and then it starts to space out a lot. And that's not normal behavior. Normal behavior, you kind of tend to be crowded into the middle, that bell-shaped peak, and then less scattered over on the left and the right-hand sides. All right, so make sure you got that, and that will be the end of this video.